All right, guys, welcome back. This is a little extra video here to go with Unit 1, Section 4, called Returning a Polygon to its Original Position. This one actually is a pretty simple concept. However, sometimes it can be a little confusing just because you can get lost in the lost in all the directions of the spinning and rotating and reflecting and so on and so forth. But it's really not that hard. Don't make it harder than it is in your head. Okay, the best bit of advice I could give you here is to make sure you draw pictures. If you're doing a mastery test and the Edmentum doesn't give you a picture, they just give you like a small description of a problem or a picture, then you'd be best to draw it, and then it's just that much easier to manipulate it than trying to picture it in your head. Okay, so all right, returning a polygon to its original position is simple. It's basically any transformation that you can do, whether it's moving, spinning, or flipping, okay, an object, and then bringing it right back onto itself, or so it covers itself. So my official, I guess, first sentence here I have a kind of a definition, but this is what mapping is. When I talk about mapping a polygon onto itself, what does it mean? Mapping a polygon onto itself means spinning it, flipping it, or moving it. So the new image that you get comes right back and perfectly covers the pre-image. So it's kind of like taking something, spinning it, which would be a rotation, flipping it, which is a reflection, or moving it, which is a translation. These are terms from the last section. So spinning it, flipping it, or moving it to where it turns enough to where it covers itself back up, and then it doesn't even look like it moved in the first place. The only thing that moved would be the points, the actual letters themselves, okay? So in other words, if I just, like, I'll come back to this in a minute, but if I bring this over here, and I just take these two blank whiteboards, they're both rectangles, right? They're both rectangles. Rectangles are polygons, quadrilaterals. If I treat this as one quadrilateral, one rectangle right here, okay? If I map how much spin would it take for me to spin the top rectangle or quadrilateral clockwise to map it back onto itself to where it covers itself back up? Well, think about this. So if I start spinning it, all right, so now it's off itself, right? So if you think of the bottom rectangle as your first image, and the pre-image, and the new image is the top one, how much am I going to have to spin this to where it covers itself back up? Okay, well, obviously it's not covered up here because I can see both of them. And then if I keep spinning, and then boom, it maps on top of itself, and now it's covered up again. But the corners are not in the same location, right? Originally, these corners were here, right? So if you think this is like point A, point B, point C, and point D, right? Now they twist and turn to the point to where they're at. Now this was A, this is A prime now, because it's a move. Remember, it's prime means it moved once. A prime, B prime, C prime, D prime. Okay, they moved. Okay, well, the biggest thing you need to be able to do is to be able to measure how much of a movement was that. Remember, a spin or a rotation really is the true verbiage we should use here from geometry. Rotation is measured in degrees. The direction is counterclockwise or clockwise. That's just whether you go left or whether you go right. But the degrees tells you how much. So right now, if I spin this much, well, that's a 90-degree spin. And then if I turn this much, that's 180 degrees. It's not all the way around, although it kind of looks like it because it covered itself back up. But we know that this point here, this point right here, was originally up there. Well, in order for it to go back up there, I'd have to go the full 360 degrees. Right? This would be 270. And then go all the way back up here, right, is 360 degrees. Maybe that's best to be exemplified if I put a point, right? I just put a simple point there to keep track of where I'm at. Okay, 90 degrees, and it's not covering itself up. At 180 degrees, it maps back onto itself, right? But it's not in the same location, and that's fine. All I'm asking is, how many degrees does it take to map the top one on top of the other one, on the one underneath, so it covers it up? Well, it takes 180 degrees, right? Now I could go 270 degrees, and then 360 degrees obviously maps it back onto itself as well. But what would we say is the minimum? What's the minimum angle of rotation? 180 degrees. Okay. Now that's pretty easy to do with rectangles, but we need to be able to do that with other polygons as well. So I have drawn here, and it's a little faded out now because I just spun it a bunch of times. But I have a regular octagon. And another thing you need to understand too is, if it hasn't been defined for you in Edmonton yet, is the word regular means that the sides are all the same length on your polygon. Okay, because you can have irregular polygons and that changes things. But on a regular octagon, octagon has 8 sides. On a regular octagon, it has 8 congruent or 8 equal sides. Congruent geometry just means equal or the same length, same measure. Okay. Now this point here is my point of rotation. I'm spinning. It's basically the center of the polygon. So I'm now, before when we did rotations, we were spinning whole shapes like triangles. In Unit 3, we're spinning triangles around like this, around. Now we have the point inside of the polygon. We're going to spin it around that point more like a clock really than anything. So if I have a regular octagon here, first of all, you need to determine how many sides there are. There's 8. That means there's 8 angles as well. One thing it's going to ask you here, and it's what I've already said myself, and I'll bring this bag out here, is the degree of rotation. This is how much you spin an image to map onto itself. Okay, it's going to ask what is the minimum degree. Actually, it'll say minimum degree of rotation that it takes to map or spin the image back onto itself. On the one I just did, the example of the whiteboards, it was 180 degrees, right? 360 took it all the way, but I could do it in 180 degrees. Well, in an octagon, it's going to be less. Well, how do I determine that in an octagon? It's a lot harder than it is in a four-sided figure, like it's a rectangle or you know, a quadrilateral. To find that minimum amount, all right, here's what you do. First of all, common sense-wise, if you just look at it, it's pretty obvious to see that, like, if I take this polygon and I treat it as a ratchet and I ratchet it like this, I know that once I get point A over here to point B, so where, let me use a different color here, where this becomes point A, and this becomes point B, and this becomes point C, and this becomes point D, and this becomes point E, and this becomes point F, and this becomes G, and then this becomes H, okay? If I ratchet it one click like that, that's going to take the polygon, the octagon, and it's going to put it right back on top of itself. So that's kind of common sense to see, but the question is, what is the degree of rotation, or how much angle do I need to twist it? I knew with the rectangles it was 180 degrees. Okay, so the question will be, what is the minimum degree of rotation? Okay, what is the minimum degree of rotation to map it onto itself? So here's what you do. First of all, I need to find out how many degrees, or how many angles there are, okay, I should say, how many angles are there in the polygon, inside, okay, and this is what I'm talking about. If let me use this, if I take from my origin, and I draw this line from A to the origin, okay, I can draw lines from every vertex point, basically, in the shape, in the octagon, to the origin. And I'm doing this just to make it more visible for you. You don't have to do it this way, but this is what I like to do. If I block this up, but what I'm doing basically is it's like taking a pizza and cutting up into its pieces. But they're going to be all equal pieces. Because the distance from that origin to every one of these vertex points is equal. It's the same distance. Which means that these angles are all the same. Okay? Whatever they are, they're all the same. Now, Okay. I do know now I can just count, obviously pretty easy, how many angles are there in there. Well, there should be 8 because this is an octagon, so 8 sides creates 8 angles. 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. Now, we know what one full rotation is, right? That's just based on the rotation of degrees in a circle, right? The spinning of the hand of a clock, all right? If I spin in a circle from start all the way around back to the start, that's 360 degrees, all right? 360, okay? Well, if I take a 360 degree rotation, which is what a full rotation is, and I divide that by the number of internal angles or interior angles, okay, which in this case we know it's 8, so 360 divided by 8 is going to give me what one angle measurement is, or what one angle degree movement is. In this case it's 45. 360 divided by 8 is 45, or 45 degrees. 360 degrees divided by 8 is 45 degrees. So each one of these angles, or each one of these pie pieces here, is worth 45 degrees of rotation. Okay? So if I take the polygon and I ratchet it one time, so A ends up at B, turn every one of them 1 point away, you're moving 45 degrees. And that takes A to B, B to C, C to D, so on and so forth all the way around the polygon. So the minimum degree of rotation here is the amount of degrees of spin it takes to get this point to that point. Okay? So you need to be able to do that. And another thing they might ask you is how many times will the image map onto itself if you were to go ahead and determine to spin and rotate A all the way around back to itself? Well, the answer there is 8 times, because of the fact that it has 8 different vertex points to land on until it gets back. Okay? So it's not that hard. You just need to understand how to find those minimum degree of rotation, or that minimum amount of spin, which in this case is 45 degrees. Okay, and an octagon, a regular octagon, obviously it changes if you have a decagon, it's 10 sides. Whether it's a heptagon or a hexagon or so on and so forth. Okay, last little thing I wanted to mention here that you'll have to be able to do too is another way of mapping an image onto itself. There's a couple other ways. We just did rotation. You can just translate or move an image and then move it back to itself. That's kind of a common thing to do. But the more tricky one of the one is that I would say you'd probably need a little more help with would be reflecting an image onto itself. So this is where you have to think back about what a reflection is. A reflection requires a line of reflection or line of symmetry. So on the bottom here, remember, a line of reflection is, they're asking you to, if they ask you to find the line of reflection, what line cuts through the image and gives 2 symmetric halves. So to exemplify this, let me put that back on there just so you have it, see it long enough in case you wanted to write it down. So they're going to give you an image and they're going to say what line of reflection allows the image to reflect back onto itself, or reflect and map back onto itself. Okay, so you're looking for a line that will cut through the image and makes that image 2 separate, symmetric, perfectly equal or congruent halves, that if they were to reflect, they would reflect right back on top of itself. Okay, now a lot of images have more than one line of reflection, and then there'll be questions like that. It'll say, how many lines of reflection does image A, B, C have to reflect onto A prime, B prime, C prime, or so on and so forth. So if I take a triangle like this, let's see, let's go here. And we're going to go here. This is a pretty common thing. If I have triangle A, B, C, okay, what line of reflection would allow triangle ABC to reflect back onto itself or map onto itself? Well, it'd be this line of reflection right here. Okay, which in this case happens to be the line. Remember, this is the x-axis and this is the y-axis. So this is at 1, 2, 3, 4, 5, 6. This is the line x equals 6. So the line x equals 6 cuts that triangle into two symmetric halves, to where now you have A and B. If you rotated, or excuse me, reflected it about or across the line x equals 6, it would map back onto itself. So A would end up over here. Okay, in other words, now we know that. So like our movement, if A comes over here, this would become our A prime. This would become our B prime. And then C prime would still be right where C is, because it happens to lie right on the line of symmetry, so it doesn't move. All right, so that is a line of reflection. And there is multiple lines of reflection sometimes. This one here happens to only have one. Let's take a parallelogram. So let's go back to a quadrilateral here. Let's go. All right, so here we have a parallelogram. Parallelogram, quadrilateral, 4 sides, 2 pairs of parallel sides, opposite sides are parallel. How many different lines of reflection does this have that allow it to map back onto itself? Okay, so again, this isn't a rotation like the octagon. All right, this is a flip. How can I flip it? In what way can I flip it to map it back onto itself? All right, well, I see one right here. If this is, let's give these vertex points some names here. So this is point A, point B, point C, and point D. Okay, I see one right here. And the most common ones here, or the most common verbiage for this, is the diagonals. The diagonals here will allow the parallelogram to map back onto itself. So if I go through here with this line, which is a diagonal line, all right, that allows it to map back onto itself. Okay, if you reflect it across the line. All right, same thing with if I come through here like this. Oh, I missed that a little bit. Okay. So if you reflect it across either of those lines, it will map back onto itself. So that has 2 lines of reflection. Okay? Now there would be different kinds of problems on your mastery test that will combine some of this material, and it might be rotating and reflecting. Oftentimes you'll have problems where you have 2 shapes together, one shape inside of another shape, and you have to look for the line of reflection that allows both shapes to map back onto themselves together in unison. So pay attention to that. I don't think it would take me an hour to show you all the possibilities here, and I probably still wouldn't hit them all. But if you just use common sense, use your head, and draw it out if you have to, I think you'll be just fine. All right, let me know if you have any questions. Remember, you can always email, call, or text. You have my info. So until next time, good luck.